Good morning to all of you, and today we will start this morning session where we will discuss the conservation of angular momentum, the application of Reynolds transport theorem. Last class regarding the Reynolds transport theorem, yesterday morning session, we derived Reynolds transport theorem and we explained Reynolds transport theorem related to conservation of mass. We explained Reynolds transport theorem related to or applicable to conservation of linear momentum, and also we explained that when the linear momentum is described with respect to a non-inertial frame of reference or the control volume where the frame of reference is attached is moving with an acceleration, then how it is modified. Today the same thing we will discuss with respect to the conservation of angular momentum. Let us write then conservation of angular momentum. Conservation of angular momentum. Okay, conservation of angular momentum. Now, again by this similar line, in the similar line, we write the property n as we described in Reynolds transport theorem. In this case will be the angular momentum. How do we write the angular momentum? Angular momentum is written as this. This is the definition of the angular momentum, which is the moment of the momentum about a point from where r is the radius vector to the point where the momentum is defined. Okay, so this is the expression for the angular momentum, which is the moment of the momentum. So, if n is such, then what is eta? Eta is n by m, we know. So, therefore, eta is therefore r cross v. Well, now if I write the Reynolds transport theorem, then what it will be? Then it will be d dt of, if I write d dt of this thing, the n, that is the angular momentum r cross mv. Now, before that I tell you first, let us take that the angular momentum is described first with respect to an inertial frame of reference. That means which is at rest or moving with uniform velocity. Let us, for our understanding, simple case that the inertial frame of reference is purely the static frame of reference where we define the angular momentum, that both the radius vector and the velocity. So, therefore, now if this is so, the way we did for linear momentum also, this is for the system equals to, as usual by our Reynolds transport theorem, the rate of change of angular momentum within the control volume. What is that? Rho into per unit mass angular momentum, that is r cross v dv, plus the net rate of efflux of the angular momentum from the control surface Cs. What is that? That is again eta, that is angular momentum, times v r, the relative velocity with respect to the control volume, as we already did, that is the flux. Flux is always defined like this. Well, so therefore, this is the rate of change of angular momentum of this system, rate of change of angular momentum within the control volume plus net rate of a flux of angular momentum from the control volume. In a similar way, if we write this by taking care of the variation of the velocity and the momentum within this system, it is another way of writing. People write like that, d dt of, we can write this thing integral of r cross, considering an elemental mass where the velocity v is defined and the radius vector r over this system. When we take consider the, it is varying. Now, if we take d dt inside for the continuous variable, we can take d dt, then dm, any elemental mass, is invariant with time by the definition of the system, that is control mass system. Okay. Then we can write, it is very simple, slowly we will go d dm. That means, if we consider this is varying within the system. So, this thing can be written by integrating things like this. Now, if we differentiate, the first term will be dr dt cross v, that means if you differentiate it, I write it here, dr dt cross v plus r cross dv dt dm. Now, dr dt is again v. So, v cross v, you understand, dr dt is what? Dr dt is again v. So, therefore, v cross v is 0. So, therefore, this comes equals to, these are all. So, this becomes equal to, this is system, this becomes equal to, this becomes equal to only this term r cross dv dt dm, and that is for the system. And this is nothing but the same thing, that is the rate of change of angular momentum of the system. This can be written like this, rate of change of angular momentum of the system, by consideration of the fact that angular momentum may vary from point to point within the system. This can be written in terms of an integral sign within which this is there. So, however, this is over the system. The two terms are same and they define, these terms define the rate of change of angular momentum of the system, where the angular momentum, that is the velocity and the radius vector, is described with respect to a static frame of reference, as I have told earlier, or an inertial frame of reference. And by laws of physics, we know the rate of change of angular momentum of a system, that is a control mass system, is equal to the sum of the moment acting on the system, sum of the moments acting on the system, which causes the rate of change of angular momentum of the system. Similar to the linear momentum, that rate of change of momentum of a system is equal to the sum of the forces acting on it, which cause the change in the linear momentum. Similarly, rate of change of angular momentum of the system or of any system equals to the sum of the moments which cause this angular rate of change of angular momentum, and this is basically the law of conservation of angular momentum, law of conservation of linear momentum applied to a system. So, therefore, left hand side becomes sigma m, sum of all the moments. Okay. Now, I write it again. Now, I write this, therefore, this expression becomes sigma m becomes equal to what? Becomes equal to del t of, then I write rho r cross v, okay, dv plus over the control surface rho r cross v times v r, that is the relative velocity, dot n d. Again I am writing this. What I have done? I have substituted the sum of the moments in the left hand side when these r and v are described with respect to a static frame of reference or inertial frame of reference. Now, what happens if I change it to a moving frame of reference? Now, one thing I tell you, when I derive the linear momentum conservation, then we took an inertial frame of reference where the frame of reference is only accelerating. This is because I told that it is for our simplicity of analysis, we want to describe every parameter with respect to the control volume. For example, the flow rate can be found out by multiplying velocity with area and density, where the velocity is the relative velocity, that means velocity relative to the control volume. And in many cases where we are concerned with linear momentum only, with the rectilinear motion control volume, for example, the jet engine, the rocket I told you yesterday. But in case of angular momentum, the system or the control volume in practice has a rotation which causes the angular momentum. Now, you consider a pump, you consider a turbine, you consider a compressor as the equipment, this is rotating. So, therefore, now we will consider an non-inertial frame of reference which is also rotating along with its linear acceleration. That means, now if we have for example a static frame of reference, let us define as capital X, Y, Z, we consider a control volume which is rotating. That means which is having a linear acceleration, linear velocity of the control volume, linear acceleration of the control volume A, along with that control volume is rotating. Then we consider, if we attach an axis, we consider an axis like this X, Y and Z which is rotating with an angular velocity. That means here we consider this way, this control volume is rotating. That means if we attach the axis of reference to the control volume, this is along with its rectilinear motion and acceleration is rotating with an angular velocity omega. Now a very general relation I will show you, that how we can describe, relate things described in this inertial frame of reference. Let this is the inertial frame of reference, static frame of reference, with that described in this moving frame of reference which is attached to the control volume, which is having a linear motion and acceleration along with angular velocity. Now here we first write the expression first of all, then I will tell you. First expression is that I just write the expression, if I write V with respect to this X, Y, Z, that means with this frame of reference, it becomes V static frame of reference minus this. This I define as the, for our easier understanding, is the velocity of the control volume, that means the velocity with which the frame of reference is moving. And this small x, y, z is our relative velocity, that is the velocity described in this frame of reference small x, y, z, and this is big x, y, z is the static frame of reference, inertial frame of reference. This is the relative velocity with respect to the control volume minus omega cross r. When there is no angular velocity, this term becomes 0. So, it becomes simply the relative velocity or velocity reference to this x, y, z axis is equal to that with respect to the static frame of reference minus the velocity of this control volume or the velocity of the frame of reference attached to the control volume. This can be derived, just I tell you for your understanding, that if we take a point here with respect to this x, y, z frame of reference, and if we show this point as a radius vector r with respect to this frame of reference, static frame of reference, and if this point is described by this radius vector, which is this one, which is small r, that means that is described with respect to the frame of reference attached to the control volume or moving frame of reference, then one can write, if I show that this distance, that is the origin of the static frame of reference and the origin of the moving frame of reference is separated by a radius vector r0, just a guideline for you that one can write from the vector addition r bar is equal to r0 plus r. That means the radius vector of the point with respect to the static frame of reference equals to the radius vector of the origin of the moving frame of reference from the static frame of reference plus the radius vector described in the static frame of reference for that point concerned. Let the point be P. Then if you differentiate it with respect to the static frame of reference, then what happens? X, y, z, b. Then this is the distance of separation, that is from the origin to origin. This becomes is equal to dr0 dt. there is no frame of reference, but this is dr dt x y z. Now this is what? This is our v c v. This is what? This is our v, the absolute velocity, that is velocity with respect to inertial frame. Now this can be written as dr dt with respect to the moving frame of reference that is attached to the control volume, since this moving frame of reference or control volume is moving with the angular velocity omega, it is omega cross r, and this equals to this 2. This is found by a theorem that is known as Chesel's theorem. The proof of this I am not doing here. If you are interested, you can see in my book, it is done. So therefore we see that this equal to velocity of the control volume plus the relative velocity with respect to the control volume. That means the velocity dr dt is the velocity described in this frame of reference, moving frame of reference, plus omega cross r. So when omega is 0, Vxyz is Vcb plus Vr. That means the Vr, the relative velocity, is a vector, is what? V absolute velocity, Vxyz, which we call earlier as absolute velocity. This we used earlier in the linear conservation of linear momentum, where we considered that omega is 0. That means there is no rotational movement of the control volume. But here there is a rotational movement of the control volume. Now with this, one can write by taking a second derivative of this about the acceleration in the similar way. One can write this thing, that I will not displace this. So if velocity is this, if the velocity is this, I think you can see. This is Vr is V when omega is 0, when omega is 0, omega is 0. Now again I am writing, don't worry. So therefore what we get? We get that for velocity we get that V of xyz, which is our relative velocity, is the V of capital XYZ, means absolute velocity, reference to inertial frame of reference, minus the velocity of this Cv minus omega cross r. This Vxyz is our Vr and this is V. So therefore we can write in our nomenclature minus. Similarly for acceleration, one can get not directly by differentiating this, you have to come through. I tell you a hint, if you can do this, is for your exercise, it is done in my book also, that you have to make the derivative here, and then applying the Chesel's theorem, one can get that Axyz, which is equal to dv xyz dt equals to dv, that is the acceleration with respect to the inertial frame of reference, minus dv cv dt, that is the rate of change of velocity of the control volume, minus 2 of omega cross V described in the moving frame of reference, minus omega dot, that means d omega dt, cross r, that is the cross product, minus omega cross r. So now we can write from in our nomenclature, this is the acceleration relative to the control volume, that becomes equal to the acceleration with respect to a inertial frame of reference or static frame of reference, actual acceleration and absolute acceleration minus the acceleration of the control volume minus 2 omega cross, this is relative velocity reference to the moving frame of reference, minus omega dot. Dot is what? Dot is d omega dt. Omega dot is d omega dt, rate of change of angular velocity, and this remains as it is, rate of change of angular velocity. Here you observe one thing, that when omega is 0, all these terms are 0. When there is no rotation of the control volume is not rotating, that means the frame of reference is not rotating, non-rotating frame of reference, acceleration is equal to the relative acceleration, that is acceleration with respect to control volume is its absolute acceleration, acceleration described in inertial frame of reference or static frame of reference minus the acceleration of the control volume. This part is true, this becomes 0, which we used for linear conservation of momentum. But here we have to now replace this. So it is very difficult to handle with all these terms. So therefore we write A relative is the absolute acceleration described in static frame of reference minus all these things together we defined as, this is A in the absolute, AR, let us define, this is minus the containing all these things we defined as A1, for example, the vector, all this quantity defined as A1, which becomes A1 equals to then, A1 equals to then the acceleration of the control volume minus this quantity, again I am writing omega plus, now this will be plus, correct, cross VR plus d omega dt omega dot, this is the representation, plus omega cross r. So this is the A1, then AR is A minus A1. When omega 0, this A1 reduces to simply the acceleration of the control volume. Now if we substitute this in the term, now what we do, we just replace the angular momentum equation, the term d dt with respect to the axis which is rotating, and also that means I will tell that this is the thing, that means now this is the equation. Now this equation I will express this in terms of small xyz, small xyz, small, this is already VR, and this small xyz means the with respect to the axis which is rotating and also have a linear acceleration. That means with respect to the control volume, which we call at VR. Now if we write that, then what we will get? We will get for the system, we will get, what is this? That R cross T V R dt dm for this system. So what we are doing? We are just replacing by this relative velocity, the way we did earlier for the linear conservation. Now we define the momentum, everything with respect to the moving control volume and rotating control volume, where VR we are using as our nomenclature, plus over the control volume, this is over the control surface, what is this? R cross V R, and as usual VR dot NdA. So again things come, what is this? Can we write this as the sum of the momentum? No. Why? Because this becomes is equal to R. If we write in terms of the acceleration, this is the relative acceleration relative to the control volume. This is AR. What was this? A minus A1. As I described A1 earlier, this is this. Clear? So, this can be written as, therefore, R cross dVr dt, I am sorry, R cross. So, this can be written as, this is for the system. Okay. So, this can be written as R cross A system minus R cross the radius vector A1 dm. This is also dm, I am sorry, dm minus this. This part remains as it is. Now, here you see this is the rate of change of angular momentum, where the angular momentum, okay, this is the acceleration, that is the rate of change of velocity. So, this is the moment of the momentum where this r and a are referenced with respect to the inertial frame of reference. And because of that, I have substituted this A1. Again, I am showing you the last this, you see that the acceleration, when we just change with respect to this, then this become equal to this minus this quantity. When the rotation, there is no rotation of the axis, non-rotating axis, all omega quantities are 0, this becomes simply this minus ACB. So, A1 contains only ACB. A1, I am representing all these terms as A1 vector. That is some acceleration vector which contains all these terms. All are acceleration terms. When omega 0, this becomes simply ACB, which we used earlier for linear momentum when the reference axis did not have any rotation. Now, with rotation, it is A1. This always you have to remember side by side, so that you can write that this again by the law of physics, that the rate of change of angular momentum is equal to the sum of the moments imposed of the system which cause the angular momentum change. So, therefore, similarly by the conservation of angular momentum of a system, control mass system, where the angular momentum is described with respect to an inertial frame of reference, is sigma m, it stands as usual, but with a system with a modification, modified term r cross A1 is an acceleration vector which contains number of terms. In case of the non-rotating reference frame, these terms boils down to the acceleration, linear acceleration of the control volume. Now, we write this as control volume with the same logic, that when delta t tends to 0, as I have told again and again in the derivation of Reynolds transport theorem, whatever happens to a system happens to a control volume, since system and control volume coincide. So, therefore, sigma m, that is the moment acting on the control volume, minus this equals to the same thing, is that rate of change of angular momentum within the control volume, where the angular momentum is described in non-inertial frame of reference or moving frame of reference, plus the net rate of momentum, angular momentum, a flux from the control volume, where the angular momentum is described with respect to an non-inertial or the moving frame of reference. So, this is all. Now, what I will do, I will solve certain problems for you. Now, what I will do, I will solve some problems. Let us consider an application. Yesterday, we described the Reynolds transport theorem in relation to a non-inertial frame of reference, which is accelerating, but with a linear acceleration, rectilinear acceleration. That means there is no rotation. Rectilinear acceleration, there is no rotation. I think the word linear here should be replaced by rectilinear, so that you should not have any confusion between linear and non-linear from mathematics. So, it is a rectilinear acceleration. Acceleration takes place along a line, straight line. There is no rotation. So, therefore, if I take this example, now let us consider a rocket, example of a rocket. Now, how the problem is posed? Let us consider a problem is posed like this. Let us consider a problem is posed like this. A rocket looks like this. There is a nose of the rocket is like that. At the tail end, there is a convergent divergent nozzle like that. Now, rocket is moving up with a velocity v, which is a function of time, and the mass m of the rocket is also a function of time. So, v and m is at any instantaneous velocity v and m. Why the mass of the rocket changes with time, I tell you. The velocity changes with time. This is the gravitational direction, it is going up. This is because any system which accelerates, its velocity will change with time. So, mass of the rocket changes with time. This is because rocket does not take air from the atmosphere. That is why rocket is not termed as air breathing engines like our internal combustion engines or aircraft which takes air from the ambience. So, instead what happens, rocket carries both its fuel and the oxidizer required for the combustion within the rocket, which together is known as propellant, and this is carried either in the form of the solid or in the form of the liquid, depending on which we tell is a liquid propellant or the rocket propellant. I am not going into that details, but only this thing should be known that the fuel and oxidizer combinedly known as propellant for rocket is carried by the rocket. So, rocket does not have any relation with the ambience in terms of taking the air from the ambience for its combustion of the fuel. So, what happens when the fuel is burned, the combustion products or the burned gases are continuously escaping with high velocity, creating the propulsive thrust, and as a result the mass of the propellant is getting reduced, and since the mass of the propellant makes the major part of the rocket's weight, so the mass, so the mass of the rocket goes on changing. So, this is the physical concept, I think all of you know very well, for which the mass is changing. So, we consider a case in that the rocket is moving with change of mass. This is an unsteady problem which is a function of time and goes with a velocity also which is a function of time. And the problem is defined this way, that it escapes a jet whose velocity is VE, exit velocity, constant, uniform velocity VE relative to the jet. You write it, I am not writing everything, relative to the jet, and with a constant density across this area A. And this problem is also specified by a mass flow rate m dot E, which will definitely be equal to V rho and the area of the nozzle outlet. That means nozzle outlet area is A, this is rho, these are all specified, and V, so that product of these three gives the mass flow rate. So, mass flow rate ME is given, V is given. ME is V into rho into A, and we will consider rho invariant with across this area. So, this way the problem is specified. We have to find out what is the function of V with T in terms of these variables. How to solve this problem? First of all, let us apply the conservation of momentum to this system. Conservation of linear momentum. Rocket does not rotate, it is just moving linearly with a rectilinear acceleration. Then what happens? If we write this, you remember 0 is equal to, the first term was del del t. Now, here one thing is very important. Why I am solving this problem, I will tell you how to do this by writing the equation with respect to a non-inertial control volume. As I have told that we always define the parameter with respect to the axis small j, with respect to the axis attached to the control volume, that means with respect to the control volume x, y, z. This is because here also you see the velocity is defined relative to the control volume, means relative to this axis. So, therefore, if we see, and we can define at the same time a axis for understanding capital X, Y, Z as the static frame of reference, that is the inertial control volume. Then del del t of rho dV. Again I am writing again and again, by writing again and again, so you will remember it like anything, plus rho into VR dot N dA over the control surface. Now, rho dV as a whole is the dm, that means this becomes the mass of the control volume, and since mass is not changing with time, a mass is changing only with time, sorry, only with time. So, this is dmCV dt we can write, and this mass of the control volume, we take the control volume like this. We take a control volume circumscribing the rocket. This is the control volume. We take the control volume circumscribing the rocket and write this. So, therefore, this mass of the control volume is the mass of the rocket, that I will come now, plus what is this term? Let us consider rho. Now, what is VR? VR is the velocity relative to the rocket, and it is already defined this way, that it is coming outward, that means in the downward direction, vertical downward, with velocity v. Let us define by our convention I, j and k as the vector. So, what is VR? VR is coming down with a velocity ve. So, VR can be written as ve j with a minus sign, because it is coming downwards. Dot, what is the implication of n? Physical significance is the unit vector in the outward normal direction, which is again minus j. So, therefore, minus j dA. So, therefore, this becomes equal to dmCV dt, then minus j dot minus j, j dot j is 1. So, minus minus plus 1, rho v is constant by the definition of the problem. We can take rho v out and then integral dA over the control surface. This is the control surface, is this, the outside, the outer area of the nozzle, nowhere there is any flux. So, therefore, it is simply the area A, that means plus rho VE into area A, and rho VA is defined as m dot E, that means we can write, therefore, this is as m dot E, that means the rate at which the jet is coming out. Then we can write dmCV dt is equal to, if you replace this at m dot E and take on the other side, minus m dot E. Is this m dot E, that is the rate of mass efflux, is constant at this outlet section, okay, of the propelling nozzle, then we can simply integrate it, that is mCV is minus m dot E dt, that means minus m dot E t plus some constant A. Very simple. And if we consider at t is equal to 0, the initial time, mCV is equal to 0, then we can write this as m0 minus mCV is equal to m dot E t. This we get the relationship of mass. Now, this we write again, that now mCV I replace as m, the mass of the, I show you again, this I have got, that mCV, that is the control volume mass, is equal to the mass of the rocket. So, the instantaneous mass of the rocket is simply given by m dot E t. The constant m dot E, the mass of the rocket decreases linearly with time. Okay. Now, I write the conservation of linear momentum. Just simply I write, because I have deduced this thing and emphatically I described the thing earlier, that sigma f minus system A control volume, the control volume rather, into dm control volume, this is also control volume. This side is what? Del del T of rho, then VR, that is the velocity relative to this, dV, plus rate of momentum efflux, this is over the control valve, rate of change of the momentum, then rate of momentum. Momentum is described now with respect to the control volume, that is VR, to the VR dot NdA. This represent the volume flux. Now you know all these things very well. Now here we write this we take this side ACV, then we write sigma F control volume is equal to, again I am writing again and again dm plus del T of rho V R dV control volume plus rho, again I am writing for your understanding better, you see again and again, does not matter, we have time, NdA over the control surface. Now what is this over the control volume? If you do this, this is nothing but dV CV dt dm, and if we consider that this is constant over all the particles in the control volume, that if we think that the acceleration of the control volume is same within the control volume itself, this is the control volume, this becomes equal to, the left hand side I am not doing now, I leave it. Now I am just solving for right hand side. We can write the m of the control volume, because it comes out integral dm is the dvcv dt. That means the rate of change of velocity of the control volume, mass times the rate of change of velocity. Now here for the simplicity of the analysis, we make an assumption. What is assumption? Which is not a very correct assumption or very rational assumption, but we consider it that the velocity relative to the control volume does not change within the control volume. That velocity relative to the control volume is same for all particles within the control volume. If we consider that, and along with that the density also remains constant within the control volume, which is of course not true, but if we make these assumptions that the relative velocity within the control volume is same for all points in the control volume, so that this unsteady term in the momentum conservation, if we make 0, then the problem becomes little simple. Just for understanding we do, but in certain cases this may be a logical assumption, but I am not sure, or I cannot tell you that there may be cases, large number of cases where we cannot do it. But for the sake of our understanding, we make the problem simple by eliminating this term. Now what is this term then? This term becomes equals to rho. So this is mCV dCV dt. Okay. Now this term, now this mCV dCV dt, wait, what happened? It is not coming. Oh, now dVCV dt is the control volume, that is the acceleration of the control volume. This we can write in this way, mCV dVCV dt, and this is acting in the upward direction. That means we take the scalar magnitude of the velocity of the control volume with this j is the direct velocity, this is the unit vector acting positive direction of the y, which is upward. Now here what will happen if we do this rho Vr? Now what is Vr? If you see, the relative velocity is already described in the problem with a uniform velocity v coming downward. That means Vr is that minus j ve. What is this? This is again minus j ve Vr dot n is minus j, the outward normal direction, outward normal to the area is minus j. So just with the application of simple vector we are doing that. So this is v minus j dot minus j. So this is minus j dot product, that means j dot j1 minus minus plus 1. So v dA rho minus v, that means minus rho is constant. Why rho is constant? I told the problem is defined with constant density across the area. So therefore I take minus rho. So this V, then this rho VA, that means I write VE A into VE with a minus, because this minus is there, minus J dot minus J, J dot J day 1, minus minus 1 plus 1, so minus J. That means this is a vector term with rho VA V. So what is this rho VA? This is nothing but m dot E. This is defined parameter of the problem, that it is ejecting mass at a constant rate of m dot E. So therefore this becomes is equal to J. Now I write the left hand term. Left hand side is that we have to see again these are what are the forces acting on it. One force is mg, this is acting through its center of gravity mg. Another force is that drag force. Since the rocket is moving up, a drag is acting on the rocket, which is the skin friction drag plus mostly the form drag, which will be explained by Professor Soman Chakraborty in details, that either Professor Soman Chakraborty or Professor Ghosh Mollik, how the drag force is created because of the shape of the body due to the boundary layer separation. So sum of these two, that skin friction plus the form drag, which is the major part of the drag in this case. So sum of these two will give a drag force which is in the opposite direction to the motion. So you see both the forces D and m into g at any instant, these are instantaneous value because mass is changing with time. So weight acting on it vertically downward is changing with time. Again d is a function of time, since d is depending on v, d depend on the velocity which is a function of time. So if instantaneous values are like this, then we can write this as force as minus d plus mg J. That means we get all the terms in the y direction. That means the equation of motion is only in y direction because we are considering everything in the y direction. So therefore this can be written as a scalar equation, differential equation like this. Scalar differential equation like this is very simple, that minus d, you follow from the earlier equation, oh sorry, minus d plus mg within bracket is equal to, what is that? M, now mcb I am just replacing it by m, this vcb by v, that means the mass of the rocket, velocity of the rocket, minus m dot e v. M dot e and v are defined in the problem B. Okay. Now what I can write? M dv dt, m dv dt is equal to, you take this side, m dot ev minus mg minus d. Now I take that value, m is already, it was done earlier, that m0 minus m, that m varies linearly with this m dot et. So therefore m is m0 minus m dot et. So it is very simple, dv dt. I don't think I have to proceed any further. M dot ev minus mg minus, sorry, minus, I put m0 minus, when I am putting this, minus d. Now further simplification if we make, that without any information about drag, we just drop drag. We don't know the information on the drag with respect, because here everything in terms of the velocity. We don't know any information about drag with velocity. If we have, we will put this. Now afterwards everything is mathematics, no fluid mechanics is there. Now for simplicity of the mathematics, and since I do not know any information, I just cancel this. Then I write dv dt is equal to m dot e. Now everything is mathematics now. M dot et b, sorry, minus g. Then this is a very simple equation that you can definitely solve. So you can take this here and dt, that you can definitely solve. That means V is equal to, that you can solve, V m dot E V E divided by m0 minus m dot E t minus G, that means this is dt minus t. Now this rather I write dv integration 0 to v. Initially if we take at t is equal to 0, v is equal to 0. Now this is mathematics. So this becomes is equal to v, and integration of this from 0 to t, you do it, this will be a log ln m0 minus m dot dt with a minus sign, and 1 upon m dot d will be coming. That means it will be 1 upon this integral simply m dot d ln, this will be minus m0 minus m dot dt. That you do. That means if you make this integration and put the limit, ultimately you get an expression, and that is the final expression. What is that expression? So let me tell them, this is very simple, that is school level things. So you get an expression V is equal to V E ln, ln will come by integrating that term m0 by m0, I gave you the answer, m dot d t minus gt. This is neglecting the drag force. So you see how we have applied the conservation of linear momentum by the Reynolds transport theorem described with reference to a inertial control volume which is accelerating, having a linear acceleration, and we get an expression for the instantaneous velocity. Okay, so this is one very clear example. Now I will solve before you one problem of application of Reynolds transport theorem to the conservation of angular momentum. Though I have given you the information about the transformation of the velocity component with respect to a non-inertial control volume which is a rotating frame of reference, but I think this will create more complications. If possible, we can solve it with respect to a static frame of reference. That for your information I have developed, that I have told you how you can transform it by applications of a theorem, and then the entire expression contains number of terms which may sometimes create complication, but you do it as an example. This is given in my books, but today I will solve rather a simple approach of solving a problem with respect to a, what is that? Yes, with respect to a inertial angular momentum conservation inertial control volume. What is this problem? The problem is like this. The problem is like this. The problem is very simple. The problem is like this. There is a lawn sprinkler. You know what is a lawn sprinkler? Which sprinkles water in the garden. There is a lawn sprinkler which has got two arms like this, and which, let us consider the lawn sprinkler is in a horizontal plane. That means this x, y is in horizontal plane, and z, this is the axis perpendicular to this plane, is the vertical upward axis, x, y and z. So this is look like that. A lawn sprinkler in a horizontal plane rotates with an angular velocity omega. Why it rotates? It rotates because of ejection of velocity. The way engine goes by the propelling force, it is a similar type of thing by ejection of velocities from two arms outwardly. This is the ejection of velocities, by which action the sprinkler rotates, freely rotates. There is no moment acting on it. This is because of the flow of water and ejecting water which creates a moment on this, and this rotates. This is the simple physics, that this is a rotation of the lawn sprinkler. Now the problem is posed like that. This is moving with a velocity omega, and this is coming out with the relative velocity Vr, and this is purely symmetrical outward Vr, and the area is A, both this side, and there is a volumetric flow Q which is divided in terms of Q by 2 both sides, and we take rho constant, so that the now volume flow rate Q by 2 can be written as rather rho A VR, because Q by 2 is rho will not there, A into VR by 2. So, total Q is rho into A into VR. That means Q by 2 coming out from one arm is A into VR, where VR is the uniform velocity of jet coming out with respect to this launch sprinkler. Try to understand, with this velocity is respect to the launch sprinkler. Q is equal to A VR. Okay. Rho is constant. Here we are not dealing much with the mass, because it is the problem with liquid. For example, water is coming out. So, it is the volume flow rate. If you want to know the mass flow rate, you simply multiply with rho. Now, you see that if I want to solve this problem with respect to a static frame of reference, okay, which is an inertial frame of reference, and there if we have to consider this VR in my expression, which is described in a non-inertial frame of reference, rotating frame of reference, how do we do that? One approach is that we can do everything with respect to a non-inertial frame of reference. That is very lengthy and little complicated. That I leave you as an exercise. This will only involve more terms mathematically, because the concept is same as I described earlier, and I know that the terms containing in the acceleration, all the terms will be taken care of. But here you see it will be much easier to deal with a static frame of reference or inertial frame of reference, let x, y, z, not this x, y, z which is rotating. So, what is this equation? You tell me that now we can write with respect to the static frame of reference, sigma m is what? Del T of, tell me, integral rho r cross v dv plus rho, this is over the control volume, r cross v and Vr dot n dA over the control surface. Well, now this is 0 in this problem defined. Now, what is this? First term. Now, term 1. Now, if I have to evaluate term 1, my first job is that this is little complicated in mathematics. We have to find out the V which is referenced in the static frame of reference. So, this V can be written from the earlier expression, as you know, is omega cross r. Now, you see here there is no rectilinear velocity plus the Vr. You remember this equation, that V is equal to Vr plus omega cross r plus Vcb. Here the control volume does not have any rectilinear motion. So, it is omega cross r. This can be considered as velocity of the sprinkler. So, sprinkler, sometimes we write it velocity of the sprinkler has got only rotational component. So, by the earlier equation, if you see that the absolute velocity can be written as relative velocity plus omega cross r, which already I told so many times earlier. So, I just exploit this. So, therefore, V will be, what is omega? Omega vector. Omega is, if we take the scalar component omega, it is about the z axis, that means the vector k. Here again I am telling that our usual notation I, j, k. Cross, now what is r? R is, that is at any location r, the radius vector, that means this can be written as r I. Now, what is Vr? Vr at any point, this is constant Vr. So, this is the magnitude Vr I. Well, so therefore, then k cross I is j. So, therefore, we can write omega r j plus V r I, omega r j plus V r I. Now, I find out this term. What is this term? R cross V. It is very simple, that means R I cross this thing omega R j plus V r. V r is defined as a constant velocity, relative velocity coming outward, that is the scalar magnitude of the V r I. Now I cross I is 0, same direction. So this becomes is equal to I cross j is k, so omega r square k. That means this r cross v vector is defined in this way. This is the sense k. Now the first term becomes, therefore, if we replace this, if we replace this omega r square k here, the first term becomes term 1. The first term become, if we replace this in there, the term 1 become, now here one thing, before I do this term 1, here everything, when I consider the right arm as the control volume, I have forgotten to tell you, because everything I can write when I define a control volume. So if right hand part, because of the symmetry, I take one arm here, right arm, let is the control volume, then everything should be multiplied with 2 when I will write this equation with the total moment acting on it. Incidentally, it is 0 here, so I will write 2. This is not 2 as the general equation of angular momentum conservation by the Reynolds transport theorem. 2 is applicable for the application here when your control volume is half of the total equipment. So therefore a 2 will come, otherwise you will not be able to understand. Then if we replace this omega r square k, then it will be integral rho omega r square k dv. Now you see omega is constant, rho is constant, this is k is this, then r square dv. Now if I write dv, that means the volume, now this is over the entire control volume. dv is written in terms of dr as the cross sectional area times the dr, that means the differential change in the radius vector. If I do that, rho omega r square a dr, k is its sense, k, then what we can do, rho constant, I told you earlier by the definition of the problem, omega constant, cross sectional area is constant. So rho omega, that means we get d dt, this is changing only with time, rho omega a. Now r square dr, now when this control volume domain, I change this dv in terms of dr, this will be 0 to r, the domain of integral, because the variable is changed, dv is written in terms of a dr. So therefore r square dr is r cube. What is this r? Capital R. Before writing that, r 0 to r means that is 0 here, and r is the arm length. I am sorry that in the problem definition arm length r is also given. Capital R is the arm length, capital R in both sides, it is symmetry, the arm length. Well, so r cube, that means this become is equal to r cube by 3, r square d and 2 rho omega a r cube, oh sorry, this becomes is equal to, now omega is constant, a is constant, r is the arm length constant. So 2 rho a r cube, 2 rho a r cube coming out by 3 d omega dt. Angular velocity is changing with time because it is freely rotating, there is no moment acting on it which balances it. So therefore it will go on decreasing. So 2 rho a r cube by 3 d omega dt. This is the first term k, I am for k. This is the sense that about the z axis, term 1. Now I will go to derive the term 2. What is term 2 now? Term 2, if you recollect from your equation, that I will show you again. Where is that equation? Yes, term 2. Term 2 is R cross V, VR dot NDA with a 2 because of the two sides. Well, then term 2 if we write, then first of all again I write here term 2, that will be better. 2, term 2 will be rho R cross V VR dot NDA with the over the control surface. Now here again if we write this V, V will be what? V will be V sprinkler, that means that is omega R as usual plus the VR. Now one thing, this is over the control surface, here the concept is there. This control surface where the efflux is there, for example here, or influx, only efflux is there, this is the control surface, it does not deal with that, this is the so therefore here the velocity relative to this is VR in this direction, okay. So therefore plus the relative velocity which will be into VRJ, that means this the relative velocity is the scalar magnitude J plus the sprinkler velocity or omega cross R, okay. Now therefore if you do that, then what you will get? Omega is as usual omega K cross R. Therefore here R is the capital R. Why? Again the radius vector, all the points here is the arm length R. Radius vector is not varying, which was the case when we integrated within the control volume for the first term. This is applicable only at the control surface, that means where the fluxes are there here. So for which the R is constant, that is the difference Ri plus Vrj. Well, so therefore we get Ikj, that means omega Rj plus Vrj, very simple, that is omega R plus Vr in terms of the scalar value J. So this is our V bar. Now if that is V, now if we do the this term, that R cross V, then what happens? Term 2 equals to, now term 2 equals to 2 into rho, what is R here? Now we have to know the R. R is what? R is R in capital R. R is capital R into I, that is capital Ri. I is the unit vector, capital R cross plus Vrj, okay. So this is all right, capital R Vrj times the, now we have to do this thing Vr dot NDA. So Vr is Vr as we have defined this Vr. Now Vr is J dot what is N? N is also J because here N is radially outward. So this is also J because our J is in the positive Y direction, positive Y direction. So this velocity relative to this is in the positive Y direction. So therefore, and outward normal is also in the positive Y direction, J times dA. So what is this? 2. Now you see rho, now omega R square I, this is J, I cross J, these are J K. So therefore it is rho omega R square plus R into VR, omega R square plus R into VR, R into VR, okay, J, and this JJ1, so this becomes simply VR, VR. So this is, you see, I cross J is K, sorry, I am extremely sorry, I cross J is K, and this is J dot J1, so VR dA. Clear? Now you see omega R square R Vr, rho, Vr all are constant. So this can all come out and make 2 rho omega r square plus r Vr. You just see that. Then Vr, then rho omega r square r Vr, and then integral over the control surface d8 means the area A. What is this area? This area as we defined here. This is the area. So this area A K. So this is the term 2 rho omega. Now I express everything with the, with Q. Before that what I do, the term 1, term 2 I have got. So therefore now I replace this, the term everything in the equation, and I get the first term was 0 is equal to 2 rho, if you remember, A r cube by 3 d omega dt k. This was, everything was with the same vector notation k, plus twice, what is the second term? Second term, this is the first term, the second term is twice rho omega r square plus r Vr into Vr A k. Now if we do not take k at all, because this is a vector equation, that means this equation is with the k direction, this there we can write it in terms of a scalar equation is this 2 rho A r cube by 3 d omega dt is equal to minus 2 rho omega r square plus r Vr into Vr A. This is only mathematics now. Now if I replace everything in terms of Q, then it becomes 2 rho A r cube by 3 d omega dt is minus 2 rho. Now you see 2 Vr into A is our Q, we define Q. So 2 omega r square into Q minus 2 Vr A is Q. Okay. So 2 minus 2 rho Vr A is Q, 2 rho, then Vr, this is another Vr, Q and Q square by 2. Okay. Or we can simply write it as Q, 2 Vr A is Q. So Q, no Q square, it will be no 2, 2 cancels. So rho Q square into R. Am I correct? Rho Vr A is Q. So you can, or rather you cut it, you rather minus omega. This is simple mathematics. You do it. If I do any mistake, inadvertent mistake, then you 2 rho Vr A is Q minus 2Q. Rho Vr A is 2Q. So this can be written minus 2 omega r square Q minus 2Q r Vr. So rho is there, sorry. Q is Vr A, 2 Vr A is Q, rho is there. So rho is there. So therefore rho is there. Rho. You see that this is a algebraic step. So therefore it can be written as A in this form. This is the equation. Is equal to minus B minus C, where this is B, this is. You see that whether I may have done some mistake here mathematically, but I do not know whether it is okay or not. You see that only thing is that I want to express everything in terms of Q, the parameter given, and the arm length R, and the omega. Okay. B omega, no, B is this. Oh, if you write omega, correct, very correct. So rather better you write omega is the variable B omega minus C, where B is only minus 2 rho r square Q. So B is 2 rho r square Q. Sorry, entire thing cannot be defined as B, this will look bad. So this now becomes a differential equation, ordinary differential equation, linear ordinary first order differential equation. Linear ordinary first order differential equation with constant coefficient. Nothing can be simpler than this. Ordinary linear first order differential equations with constant coefficient. This can be solved. Now, this is mathematics, but how you see we derived this. That means we started with this principle with respect. Now, if we have to do this, solve this problem with respect to a static frame of reference, your only attention will be that if you have to utilize the value given in the problem, here is the concept, given in the problem with respect to this rotating frame of reference, that means with respect to the control volume. When volume flow rate is given, it is given by A into VR. That means this velocity, ejecting velocity, is with respect to the sprinkler. So therefore, what we have to do, we have to change this velocity in the angular momentum described in the static frame of reference or inertial frame of reference with that to the, with respect to this moving frame of reference. That means this V is this plus this, where this is precisely the sprinkler velocity omega. This is the key point of this. And what was followed next was a simple mathematics. How do you express omega vector form? How do you express the radial vector in vector form? Make the cross product with the elementary vector algebra. This is done. But this is the key assumption. But if you analyze this problem with respect to x, y, z, then this entire form is changed. This velocity will be referenced with x, y, z. This will be the velocity relative to the control volume, but there will be huge term here, sigma m minus a1 into dm, and that thing will be a1 into dm, and that thing will be little mathematically complicated, but we have to go very steadily by solving each and every term mathematically with the application of vector algebra. Since this is a little tedious involved process only in mathematics, I am not doing it now. I leave it to you as an exercise. Here I do it, this problem with this concept, that how it is transferred to with respect to the non-inertial frame of reference by simply substituting this with these values. Okay. So this is an application, and linear conservation of momentum. There are plenty of problems which may be discussed afterwards, or we will upload you. You please go through your textbooks, but I tell you that this Reynolds transport theorem is very important in fluid mechanics. Everywhere when you write the conservation equation, always we write with respect to a control volume, and there we write the statement which is known as momentum theorem, which is nothing but the conservation of momentum, whether it is linear or angular, with respect to a control volume, where we always invoke Reynolds transport theorem. And with the application of this Reynolds transport theorem, we solve various problems. Here we have solved only a problem of rocket and a problem of launch sprinkler. We can solve the problem of aircraft even moving with a constant velocity, where we use the conservation of linear momentum applied to an inertial frame of reference. There are problems where a fluid strikes a flat plate or a curved vein, and by virtue of change of momentum of the fluid passing through it, the vein moves. And this problem is analyzed by considering the vein as the control volume, where the fluid comes in one part and goes out from the other part, by virtue of which there is a change in the motion. This creates a motion, or again it creates acceleration, change in velocity, both linear and angular. Angular is in case of turbo machines. I already told that in case of turbines, in case of compressors and fans. I will describe this thing again when I will teach you fluid machines. There also the angular momentum change is there, by virtue of which there is a rotational motion of the equipment, which in our mathematical sense is a control volume. Sometimes the moment is imposed on the control volume, sometimes moment is derived from the control volume. So all this analysis of the practical equipments in terms of its rotation by the application of the momentum caused by the flow of fluid and its change of angular momentum, or its impressed force caused by the change of the linear momentum flowing through the device, is analyzed with respect to a control volume, which is the device itself, and by invoking the Reynolds transport theorem. So therefore, Reynolds transport theorem makes the pillar of the analysis of all such problems in the gross manner, in the integral manner, not writing the differential equation. In the integral equations where the problems are posed or we are provided with the gross values, that this is the average flow at the inlet, this is the average flow at the outlet, or uniform flow at the inlet, uniform flow at the outlet, and this is the total mass flow rate or volume flow rate. So, this type of problems are very important for engineering analysis of engineering problems in practice. Please remember it. Okay, thank you. Oh, time is there. I think I have nothing to tell you, teach you now in this session. So, we have some 10-15 minutes time. We can, yes, take some questions better. But this question, please limit it to this today's study or yesterday Reynolds transport theorem. Don't go beyond that, because I can tell you, but unnecessarily, because there will be a question answering session at the end of the day. Okay.
RTT 1295.
1295. Yes, please. Yes, please. Hello? Not audible. Not audible, you go to another one.
1241.
1241. Yes.
Hello.
Yes, 1241.
Hello.
Hello.
Sir, good morning.
Good morning.
Tikopati speaking from NRI Group, sir.
Okay.
Sir, my question is that how to find out. Hello.
Hello, please.
Yes.
Yes, please.
Question is that my question is that how to find out impulse momentum equation and power from this turbo machine and hydraulic steam turbine, gas turbine, and air compressor.
The question will be answered fully when I will teach turbo machines in last 3 sections. In last 3 sessions I will teach turbo machines, this will be told detailed. The same principle will be applied, the rate of change of angular momentum, which equals to the momentum, the sum of the moments applied on the machine. The same thing which I have done today in the problem will be applied in case of turbo machines, which will be made clear to you when I will teach turbo machines. That is nothing different. We take the turbo machines at the control volume, any impulse machine or reaction machines which is rotating and developing external torque, by virtue of which we get external power. You know, torque into angular velocity is the power. So, you find out this torque or the moment which we get by these turbo machines, or torque or moment which is be given in the turbo machines if it is pump or a compressor, by just the similar applications of the rate of change of angular momentum with the Reynolds and by the application of Reynolds transport theorem, as we did. It is as simple as that.
What is the application of the impulse momentum equation in different turbo machines?
What is impulse momentum equation? What is impulse momentum equation? This is the conservation of angular momentum. The application is that to find out the energy developed by the turbo machines. We want to know the energy developed by the turbo machines. If the turbo machines flow rates are given, then you have to find out the energy developed by the turbo machine. This is the application. The turbo machines, the energy developed by the turbo machines, you have to apply these equations. You understand? I tell you, you please wait. In the class of turbo machines, I will explain these things in detail. It is not very easy to understand. Okay, hello. I tell you now, if you are very much interested, I tell you, in turbo machines, if the flow field within the turbo machines are solved, so that we get the velocity field at the outlet for a given velocity field at the inlet, you understand, then with the application of this Reynolds transport theorem, that is the conservation of angular momentum, we can find out the energy developed by the turbo machines if they are turbines, or the energy taken up by the turbo machines if they are pumps and compressors. That will be discussed in our fluid machines class. Okay, it is clear?
Yes, sir. Thank you, sir. Sir,
Okay.
my question is rather
Please tell.
1330.
1330. 1330. Please tell.
Hello, sir.
Please tell.
Provide the book you have. Please provide the book which you have used for the neural transport theorem.
There are many books from, you can see number of books are there. What book I will tell, number of books, but this should be a good text, standard textbook. Please, my advice is there that one of the objectives of taking classes by us is to benchmark the fluid mechanics education in the country. Please don't read bad books. Actually, you read books of well standard. There are books by Frank White. There are books by Fox McDonald. Please write. Exact title of the book I cannot say, Introduction to Fluid Mechanics or something like that. Along with that, my book is there, Introduction to Fluid Mechanics and Fluid Machines by S.K. Som, G. Vishwas and Suman Chakraborty. You read any of these three books, books by Frank White, book by Fox McDonald, Fox and McDonald. The exact title of the book I cannot tell, Fluid Mechanics or Introduction to Fluid Mechanics, and my book Introduction to Fluid Mechanics and Fluid Machines. You can get in all standard book, you can get it in the book by Sames. I am telling you, you go to a library and find out good books. My book is there, you can see Introduction to Fluid Mechanics and Fluid Machines, most of the things you will see there. But don't read a book below standard where all these informations are not there, which are very much required for today. Otherwise, you cannot analyze in details the systems in practice.
One
1103.
Hello.
Hello, 1103.
Good morning, sir.
Good morning.
Sir, hello.
Hello. Hello.
Yes, sir. My question is related to the derivation which you have derived for the.
Yes.
Yes, sir.
Yes,
Hello?
please, please.
Sir, my question was. Yes, sir. My question was regarding the derivation you have derived in morning for the rocket propeller. At the t equal to 0, the control volume of the rocket propeller should be m naught.
Control volume of the rocket propeller.
Mass.
At t is equal to 0, mass is m0. M0. M0, that is the initial mass.
Yes, sir. But yes, sir.
Uh,
And for the change of mass flow rate, we should write m minus m naught instead of the m naught minus m.
I am not writing at any instant mass is m, that is the instantaneous mass. Why it will be m minus m dot, then what is m? At any instant mass is m, that is instantaneous mass. You understand what is meant by instantaneous mass? At any instant mass is written as instantaneous mass m. This is the simple mathematics being taught at school level, instantaneous mass m, which has a relationship with the initial mass with time, that is being derived. Okay? So at any time mass is instantaneous mass m, which is less than m0, which may be more than m0, that depends upon how does it vary with time. Okay? You have understood?
Okay, sir.
Simple.
Yes, sir.
Okay, please read simple mathematics at school level.
1131.
Good morning, sir.
Please,
In today's discussion,
Yes, yes.
The last step is I think we have missed the constant term.
Miss the
We have missed one term, constant term, that is 3 by 2 rho a r cube.
no, that is there with d omega dt. That is there with
Problem.
here. This one.
Yes.
Yes, this is there.
Yes.
This is A. Okay. This is A is this, d omega dt. This is simple mathematics. If something is missed, you can make it. This is A. This is the concept, yes.
It is 2 rho A R cube by 3.
Hope so. I hope so if I have not done any inadvertent mistake in the algebra, yes. Yes, it is only simple algebra, yes. Yes.
The next question is,
Yes.
when you consider left part of the sprinkler,
Uh,
so that will be equal and opposite.
Opposite, yes. If you go with
Yes,
the vector
opposite.
analysis, it will be exactly equal. Term not opposite, it is equal. It is exactly equal. It will be added to that. That's why 2 is written. That is left as an exercise. Then VR will be minus VR into J. Everything will change, but ultimately if you make the operation, then the outward normal also will be minus J. So minus J dot minus J is 1, J dot J is 1. That way if you do, you will get the identical expression in scalar form, which will be just summed up or multiplied by 2. 1 is multiplied by 2. Okay, you please do it by yourself. Then only you will understand.
The sign convention for the omega.
That is omega k. Omega is the rotate. Try to understand the rotational velocity. Its vector is like that. If you represent it by scalar magnitude, the vector will be the positive direction of the axis about which it is rotating. Okay, you understand me?
Okay.
Okay.
Yes, sir, yes.
Okay, we will take question later on. We will take question later on. Now is the tea break. Okay, thank you. Okay. এত বেসিকটা এদের weak। Good afternoon. Come to this tutorial sessions on Reynolds transport theorem. So first of all, I tell you that in this session only any query relating to Reynolds transport theorem will be entertained. So please ask questions within that, the Reynolds transport theorem which have been told yesterday and today. Questions on other topic which have been told or taught, the dynamics of viscous flow and its application, which will be complete tomorrow by the first lecture of tomorrow. The tutorial for this will be tomorrow afternoon session. Okay, so therefore you ask question on Reynolds transport theorem, any query we will discuss. Please, is there any query? Don't ask questions on other topic. 1020, please. 1020, yes.
Hello.
Hello, please.
Hello?
Yes.
Good evening, sir.
Yes, good evening, yes.
Sir, I have a small question
Yes, sure.
on Reynolds transport theorem.
Yes, please.
Yesterday, you wrote the rate of the outflow and the rate of inflow.
Yes.
Then, while calculating the net outflow, you have added the two terms.
Yes.
But when we calculate net of something, we always do the output minus the input, or the outgoing minus the incoming. But in this case, it is the sum of the outflow and the inflow. So, is there anything because of anything different?
Okay. When I did it in the class, I explained this. Again, I am telling that which I did is the algebraic addition, which takes care of this difference, that A minus B, rather A plus minus B. You see, when we take the outflow or inflow, we write this in terms of V dot n dA. V is the relative velocity, for example, reference to the coordinate system, Vr dot n dA. So in case of outflow boundary, the vector V or Vr and the vector of the area dA, which is denoted by the normal outwards. Outward normal is the positive direction of the vector. So therefore these two are in the same direction. So therefore their dot product is positive. In an inflow boundary, the direction of velocity vector and the direction of the area vector, that means the outward normal to the area, are in opposite direction. So, if you represent mathematically V dot NDA, it turns to be a negative quantity when you actually compute it. So, therefore, for general mathematical expression, it is the algebraic addition of these two which takes care of the minus sign. Okay? Clear?
Thank you, sir. Thank you, sir. Yes, sir.
Okay. Okay. 1241. 1241. 1241. Not audible. One two four one. Please, not audible. Next to the, yeah. One three 1316. 1316.
Yes, sir.
Yes, please, please.
Yes, sir.
Yes.
Yes, good afternoon, sir.
Good afternoon.
Yes, sir. I'm having one question related to non-Newtonian fluid or Newtonian fluid, sir. The third solution is the Newtonian fluid or non-Newtonian fluid, sir.
What? But in this session, I will only encourage the questions on Reynolds transport theorem. Newtonian and non-Newtonian.
I know that, sir.
Now, what is your question? Newtonian fluid.
I'm having this question.
What is the question?
Third solution is a Newtonian fluid or non-Newtonian fluid.
Which solution?
Salt solution. Yes.
I don't
Salt
understand.
solution, salt.
Salt solution.
Salt solution. Salt solution.
Yeah, is a Newtonian.
Non-Newtonian fluid. So, this you better ask in different sessions. Salt solution is difficult, it is to be told, it depends upon the concentration. I think for a lower concentration of salt, it may behave as a, because you cannot tell always that a solution of this type will behave similarly in its rheological properties with any concentration. So, in lower concentration it may be Newtonian, with higher concentration it may be non-Newtonian, or it may behave differently also. Non-Newtonian fluids are of different types, time dependent, time independent, there are many other properties, okay, viscoelastic properties. So, therefore, it is difficult. In a very thick solution, the characteristics will change, okay. So, just we cannot say that any salt solution will behave as a Newtonian fluid, okay. But however, you please ask questions on this Reynolds transport theorem, okay. Next.
Okay.
Okay.
Thank you, sir.
1332. 1332. One, yes, hello.
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 Hello. Am I audible? Good afternoon, sir.
Yes, good afternoon. Audible.
Am I audible?
Yes, audible.
Hello.
Yes, yes, you are audible.
Sir, I have a question regarding Reynolds transport theorem.
Oh, sure. Ask.
We generally use this theorem to convert this system analysis to control volume analysis.
Yes.
But we generally don't. Can we use this theorem to problems of thermodynamics?
Oh,
Have you
sure.
heard of this theorem in case of thermodynamic problems?
Yes, yes, thermodynamics very much you can do, though I can tell you in thermodynamics Reynolds transport theorem is a theorem which you can apply to any physical science subjects where the analysis have to be made with respect to control volume, and we have our a priori information related to system. Definitely you can apply it. Just giving an example that The first law of thermodynamics, which is the conservation of energy, is described with respect to a system as the difference between heat added and the work done is the change in the internal energy of the system. Okay, that is control mass system. So if you want to write the same conservation of energy in a open system, in an open system, then you have to invoke the Reynolds transport theorem, and there you have to write that the net rate of energy efflux from the control volume, that means the energy efflux minus energy influx, plus the net rate of increase of energy within the control volume equals to the energy, that means that is added in a system, that is delta Q minus delta W. You understand? So therefore, in a control volume, that steady flow energy equation is derived like this. Okay, you have understood that? Okay. So this way you can write the conservation of energy to a control volume from the principle of conservation of energy to a system. All right.
One three zero nine.
1309. 1309. Yes, 1309. 1309.
Hear me?
Yes, I can hear you.
Okay, my question is, when you did these 2 or 3 examples of Reynolds transport theorem,
Yes.
the first term, dn dt of the system, was taken as 0
Yes.
both times. Is that always the case?
That
or
is-
only because it's a non-reactive system.
No, you see that the system, by its definition, mass remains constant. So whether it is reactive system or non-reactive system, if within this system mass, that means if you do not allow the mass flux across the system boundary, then the mass of the system will remain same. This is the definition of the control mass system or closed system, which we usually call as system. We do not use the control mass or the closed system, close these words as the prefixes, but we tell is system, and the characteristic of the system by its definition is that its mass remains constant. This is because there is no mass flux across the system boundary. Even if it is a reactive system, does not matter. In a reaction the mass is conserved. So if you take the mass of the reactants and the products, they are same. Until and unless mass flux is there across the boundary, the mass will be constant, and that is the definition of the system. So always we have considered dmdt is 0 by the definition of the system, or the control mass system or the closed system. Clear?
Okay, very good. Thank you.
Okay.
Sir, my question is
Yes, yes, please tell.
the control volume deforming, how to apply Reynolds transport theorem? In case of inflation of a balloon,
Yes.
the control volume it is changing. So how do we apply this Reynolds transport theorem? What
Look-
are the changes in the relation for that?
Yes. Today what
Over to you, sir.
yes, I am explaining your question. Whatever we have developed today is for today or yesterday is for a non-deformable control volume. Now control volume may be deformable, then we have to when we expand the term in the first term, when we for a particular problem that is related to a particular problem where the control volume is deformable, then you have to take care of the change of the volume with respect to time depending upon the type of deformation that takes place of the control volume. but in most of the cases the control volume is non-deformable where we apply this analysis. In all practical cases we consider the control volume as the particular equipment or appliances or a moving object like jet engine, rocket engine, where the non-deformable control volume concept goes. Okay. ঠিক আছে।
Yes. Thank you.
One two five two. 1252.
Hello.
Hello, 1252.
Hello.
Hello, yes,
Hello?
please. Hello,
Can you hear
yes.
me, sir?
Yes, yes, I can hear you.
Hello.
Yes, I hear you. I can hear you.
Hello, sir. My question is regarding. Yes, sir.
Yes, yes, please ask.
My question is regarding.
Conservation of.
Okay, sir. See, this angular momentum principle in turbo machine, sir.
Please ask.
Hello.
Hello, please ask.
We can apply this angular momentum principle for the turbo machine.
Yes,
What
very.
are the different cases we can apply this?
In all turbo machines, the basic principles of turbo machines are the.
Hello?
Hello, yes.
What are the different cases we can apply this angular momentum principle other than turbo machine, sir?
We have already given an example of lawn sprinklers today. So, lawn sprinkler is one example. So, therefore, angular momentum, conservation of angular momentum principle can apply to those systems which have an angular momentum change and have a rotation where the torque or the moments are applied by virtue of which there is a rotation, or by virtue of the rotation due to the flow of the fluid or the change in the angular momentum of the fluid, the moment is developed. So, you have to find out the application. So, there are applications even beyond the turbo machines. For example, the lawn sprinklers are there. There may be other applications also. Wherever we get this type of appliances, come across this type of appliances which either gives the moment or moment is applied on it and the fluid flows where the rate of change of angular momentum is there. But it is mostly in the turbo machines. In practical applications, you can say in engineering field is the turbo machines. That is true, mostly the turbo machines. Next. আস্তে আস্তে কোনো তারা নেই অনেকটাই 1108 1108 please.
Am I audible, sir?
Yes, audible,
Hello?
audible, please tell.
On and off.
Yes,
Hello?
yes, audible, you are
sir.
audible, yes.
My question is the what is the work transfer between heat transfer, shaft power and viscous work? What interaction between them?
See, I told you that this session I will only encourage the questions on Reynolds transport theorem. Don't ask questions from other areas, but when you are so much inquisitive, I tell you these are being taught at thermodynamics. Heat transfer, heat is an energy which is transferred by virtue of the temperature gradient. So, heat transfer and work transfer is distinctly the two different forms of energy. In classical thermodynamics, the energy transfer between the system and the surrounding is classified into basically two forms. One is the work transfer, another is the heat transfer. They are basically two different entities. Heat is an energy that is transferred because of the temperature gradient. Now, work transfer is of different kind, viscous work, PdV work, these are all there in thermodynamics. Shaft work. Shaft work is the work which is being developed by virtue of the rotation of any device or system against an external resistance, that is known as shaft power. The way the power is developed by the turbines, the way the power is taken or absorbed by the compressor, that means it is the power either developed or taken by the rotating member or rotating system against an external resistance. And viscous work or viscous power is the work which is being used to overcome the viscosity or the viscous forces or the frictional forces in a fluid flow. And this power or this work through these frictional forces in the fluid is being dissipated in intermolecular energy, which we loosely tell as dissipation into heat. Okay. So, I only tell this much. In thermodynamics lecture it is more elaborated. If you see my NPTEL thermodynamics lecture, you will see all these things, the different forms of work transfer, heat transfer, all these distinctions are there. Okay. But this is now I do not want to discuss more with this. If you are really interested, you see my NPTEL lecture on thermodynamics, where you will see the different forms of work transfer, shaft work, viscous work, PdV work, flow work. So, there are these are all work transfer. It falls into one category, and heat transfer is entirely a different category of energy transfer. Okay. Please go through my thermodynamics lectures on NPTEL. 1107. 1107.
Hello.
1107.
Hello, sir.
Hello, please.
Am I audible?
Yes, audible.
Hello.
Hello, audible.
Hello.
Hello. Audible.
Sir, I want to ask.
Please
Can you
ask.
hear me?
Yes.
Oh, I want to ask that. Sir, I want to ask that. Yes, sir, I want to ask one thing. Hello.
Yes, please ask.
Yeah. I want to ask one thing, that the flight of aeroplane wing, yes, the flight of aeroplane wing can be explained by the help of Bernoulli theorem or not? The flight of aeroplane.
Flight means what?
How it takes the flight
you
against gravity. It can be explained by the help of Bernoulli theorem or not?
now you explain
That
your.
means when it takes off from ground. Hello.
Hello, yes. When an aeroplane takes off from the ground, again I am telling this is
Pardon
not
me, sir?
audible. Yes, this is not a
Yes, my
question.
question.
Hello, do you listen to me?
Yeah, so the flight of aeroplane is explained by the help of Bernoulli theorem, means air passes over the wing and below the wing. So over the wing the velocity increases, so pressure decreases. By the help of that, the aeroplane takes up its flight. Do it is correct or not? Because over internet I found this thing, that this cannot be explained. The flight of airplane cannot be explained by the help of Bernoulli theorem. So I want to ask this thing, that is it true or false? This is what my question is.
Okay, now listen to me. Do you hear me? Look, first of all, again I am telling that I started at the beginning that please ask questions on Reynolds transport theorem. But however, when you have asked this question, I am answering, but don't take that advantage by asking questions like that, because this is by the decorum, this is the session for Reynolds transport theorem. Now I tell you, don't believe everything 100% from Wikipedia. Wikipedia writes many things which is partially true or partially false. First of all, I tell you, by a gross understanding of creation of lift for the flow of air past aerofoil can be made by Bernoulli's theorem, no doubt, because as you have told, is correct. The design of aerofoil section is such the fluid is accelerated on the top and fluid is decelerated at the bottom, but this is merely a gross understanding. Many other fluid mechanical phenomena takes place when the fluid flows over an aerofoil. There is a expansion wave takes place on the upper side of the aerofoil. There is a oblique shock takes place on the lower side of the aerofoil, and there are vortices created at the rear side of the aerofoil. So, all mixed up phenomena ultimately creates a low pressure distribution over the upper surface and a higher pressure distribution at the lower surface. This is related, this is attached to problems like that, oblique shock, expansion wave and all these things. So, it is not very simple phenomena where you can apply the Bernoulli's equation and get the answer. Moreover, Bernoulli's equation, not the modified Bernoulli's equation, but the actual Bernoulli's equation without any modification is applied only in potential flow. But these flows are not potential flow, viscous flows, and moreover the flow takes place at a very high velocity where all these phenomena like shock, expansion wave takes place. So, combinedly they decide what should be the lift force that is sufficient to make the flight or to make the aircraft to be lifted from the ground. But definitely a gross understanding from the Bernoulli's theorem may be made at the very beginning. It cannot be ruled out that it is totally false. Okay? Okay? দেখো এর মানে অন্য সেকশন থেকে কোশ্চেন ওকে ইউ আর নট অডিবল ওটা হয়ে গেছে ওই আগের যেটা কোশ্চেন করেছিল ওইটাই হ্যালো ইউ আর নট অডিবল তো কিছু বললো না অ্যান্সারটা শুনে অন্যকে দিয়ে দিয়েছে হ্যালো
Hello.
হ্যালো প্লিজ
Sir, my question. What assumptions are taken when deriving the expression of Reynolds transport theorem, and what are the practical aspects of the same theorem?
this
My question. What are this? Yes, sir.
This question has been addressed several times. The Reynolds transport theorem practical applications I have already told that today we have solved problems that to find out the propulsive thrust in an aircraft engine, to find out the acceleration of an aircraft engine, to find out the propulsive thrust of a rocket engine, its acceleration. For example, the flow through pipe, to find out the forces exerted by the fluid when it flows through a pipe or through pipe vein. What are the forces exerted when a fluid flows over a vein and how the power is developed. Angular momentum conservation explained by Reynolds transport theorem is applicable to turbo machines. How we get power or energy by the change of angular momentum of the fluid flowing through it, and it develops moment or torque by which we get power. So, all these things we have discussed several times, the applications of Reynolds transport theorem. It has a wide applications. Okay.
Thank you, sir.
Okay. Next দেখো 1039 1039 1039 not audible, please tell.
Good evening, sir.
Good evening.
Sir, what is micropolar fluid? Give some examples, and is micropolar fluid is applied to Reynolds transport theorem?
This is beyond the scope of this. Yes, Reynolds transport theorem, everything is applied to Reynolds transport theorem, which follows the laws of motions, the conservation of momentum, all the physical laws. If the laws for fluid, you see what is micropolar fluid, I am not going to explain in this session, but I tell you based on the type of the fluid the laws will be different, but so long the conservation laws are valid for a system, then the conservation of law can be used for the control volume in the similar manner, but with a different statement by invoking the Reynolds transport theorem. Okay.
Sir, there was a term Kronecker delta. What is it?
This is delta J. This I am not going, this you read a mathematics book, it is very simple. This is a typical operating functions. To show that Kronecker delta will be explained, has it not explained by Professor Suman Chakraborty when he has explained the stress tensions defining the stress field, that how do you explain sigma xx in terms of the rate of deformation. Kronecker delta, delta ij, when j is equal to I, it is 1, when I not is equal to j, it is 0. It is a simple operator type some expression. So, if you write something with Kronecker delta, delta ij means when I equal to j it is 1 and I not is equal to j 0. But do not ask this question, these are I am telling within this syllabus, whatever has been taught within this Reynolds transport theorem you ask. Okay. Okay.
Okay, sir. Thank you, sir.
Okay. Okay. Kronecker delta. One, two, five, six. Please, please.
Hello.
Hello, please, please.
Sir, good evening, sir.
Yes.
Good evening, sir.
Good evening. Good evening. Please.
Sir, in case of angular momentum,
Yes.
do we consider individual fluid particles rotation also?
Angular momentum, as I have told, that the individual, that means if you take care of this integration, yes, you can take the angular momentum of the individual fluid particle for both system and the control volume. In that case we have to integrate it, but in the solved problems we have considered that this to be constant within the control volume. Okay. That particle to particle variation we have not considered. You can consider it, you have to have an information. Try to understand, within the integral sign we have written r cross v times dv, for example, within the control volume, del del t of that thing. So, if you have got in information about the angular momentum from particle to point within the control volume, you can use it and accordingly integrate it with respect to the volume dv. Okay. Okay.
Yes, sir. Thank you, sir.
Okay.
Hello.
Hello, please.
Hello.
Yes.
Hello.
Yes, please.
One more question, sir.
Please, please.
Hello.
Hello.
Sir, morning you gave an example of rocket.
Yes, yes.
Sir?
Yes, please tell.
Are you listening?
Listening.
Sir, yes, sir. Instead of taking rocket, in the place of rocket, if you take the helicopter, the procedure is same or it is changing?
In case of helicopter, you see the difference.
This is my question, sir.
Yes, in case of helicopter, the difference is there. First of all, you have to understand the physics of the problem. In the similar way, we cannot make the analysis for helicopter. This is because for helicopter, first of all, air is being taken from the atmosphere. The engine of the helicopter is not similar to a rocket engine. The engine of the helicopter is similar to a jet engine, where the air is taken from the ambient. So, there will be an inflow along with the outflow of the jets, okay, the combustion products, the gases. So, air will come in, and at the same time there may be a steady state of the mass of the control volume with respect to the mass may be constant with time within the jet, that helicopter engine, because the rate at which air is being taken is being ejected through the nozzles, propelling nozzles, but there is an input to the input of fuel, but usually the fuel air ratio is very small, so that this change of masses we do not consider. But if you consider the inflow of fuel with some momentum, then you have to take care of that, but usually we neglect it and we consider the inflow and outflow is the same and consider the steady state. It all depends upon the definition of the problem, but grossly I can tell you there is a difference, that in case of an helicopter engine the propellant is not contained within the engine, so therefore there will be an inflow area through which the air at certain velocity and certain mass flow rate will be taken in. Okay. Otherwise the force acting, all these things will be same.
Okay.
Okay. One two 99.
Good evening, sir.
Good evening.
Myself, Professor R.C. Sharma from Dronacharya College of Engineering.
Okay, fine, please.
Sir, in the morning session,
Please.
sir,
Yes.
we have discussed the problem of rocket.
Yes.
So in this case, we have taken a quantity mass flow rate.
Yes.
Mass flow rate.
Yes.
In this problem, this mass flow rate is considered constant, because in actual practice, the mass it cannot be kept constant. Now, because we have to increase the momentum or the velocity of the rocket while launching. So in this problem, we have taken this mass flow rate constant or it is variable. And if it is taken constant, then it is all right. So if it is variable, that is actually happen in practice. So how this problem is modified? That I want to know, sir.
Okay. It's a good question. Okay, I tell you, in this problem what we have taken, I tell you that the mass flow rate at the outlet of the propelling nozzle, that is out of the nozzle, is constant. So mass of the rocket is changing because propellant is always getting depleted, because the fuel is burned with the oxidizer and the combustion product is getting out. So mass is decreasing with time, but the rate of mass flux or the velocity is taken to be constant. But the question is that if it is changing with time, the problem analysis will be more complicated. Then this will be the analysis at that instant when V, that is the velocity which you have taken, and the mass flow rate ME is defined. That in that case, this entire thing which you have analyzed, it will be for a particular instant. You understand me? So therefore, if this be the function of time, then we have to include this as a function of time, and with some complicated mathematical analysis we have to evaluate the change in velocity. It is a definitely good question. That means in the second term, that is the net rate of efflux, which has been done here with the constant velocity of ejection and which is replaced in terms of the constant what is that, constant mass of ejection or something like that, I cannot remember, that will represent the instantaneous value. Then we have to replace this as a function of time if we want to evolve a relationship of the change of velocity with time. That is the only difference. That will create mathematical complications, but the physical concept remains the same. But here, for the simplicity, definitely we have considered that at the outlet of the rocket, the rate of discharge remains constant with relative to rocket. But if that changes, things will be complicated. This will be a picture at any instant. But I feel that when the rocket goes up, the relative velocity of the jet discharging from the propelling nozzle usually becomes constant with respect to the rocket. Okay.
One more question, sir. One more question. That is a simple clarification, sir, not the question.
Yes.
But normally when we teach the students, we take this I, J and K, these are the in fact unit vectors.
Yes.
And in the notation for these unit vectors, we normally take the cap vector analysis, we normally take this psi as unit vector and having the magnitude 1.
Yes.
And if I put a arrow on any quantity, that is taken as the magnitude. If I put a arrow on I, it means the magnitude of this vector is I in mathematical notation. So if there any change in notation, sir, or something else?
No, no, it is a change, it is a convention. Doesn't matter, you can take a cap or you can put a arrow. I represents a unit vector along the positive direction of x axis, means its scalar magnitude is unity and its direction is along the positive x axis. Similar is the j cap or arrow, this is a matter of convention. The significance is same, j and k are the unit vectors along y, positive y and positive z axis. Okay. It is just a convention, you can use cap or arrow. What is that? 1165.
Good evening, sir.
Good evening, yes.
My question is, while formulating Renault transfer theorem, we have considered that control volume is fixed. What about the system boundary, sir? System boundary should be fixed or movable. If the system boundary is movable, what happens to
System?
derivation of
What I do not understand. Control
boundaries.
System is always moving. System is always moving, and control volume.
What are the system boundaries?
System boundary may move, system boundary may expand, collapse, doesn't matter. System boundary may expand, system boundary may collapse, doesn't matter. This is not mattering much. Okay, system is moving, but control volume is fixed with respect to the coordinate axis.
Oh, yeah.
Okay, but control volume is moving. In that case, coordinate axis is attached to the control volume. Okay.
Yeah, yeah. We have another question, sir.
Yes, please.
Hello, sir.
Yes.
RTT applies integral method of analysis, sir. Is there any alternative method by which is utilizing integral method of analysis, sir, except RTT?
RTT is an integral. No, RTT relates the laws of physics from control mass system to control volume system, and this is written in terms of an integral form, yes. But you have we write the integral form of the continuity equation, which is same as the conservation of mass by RTT. They are same actually. Other method means I am telling the integral method of approach takes care of the, as already explained by Professor Suman Chakraborty, takes care of the property integrated over a domain, integrated over an area. Okay, that takes care of, that is the integrated approach. When we make a differential approach, we study the behavior from point to point. When we make an integrated approach, we study the behavior on an average. For example, when you write the continuity equation and an integrated approach over a cross section, we write that rho 1 A1 V1 is rho 2 A2 V2. Inflow and outflow area are A1 A2 and V1 V2 are the average velocities over the cross section. This is one example. The integrated approach is used where when we are interested with the average behavior over a surface or over a domain. And RTT is a particular example that relates the law of physics, law of system to that of law of control volume, and that is done through integral approach only. Okay. RTT is not an integral approach. 1312. 1312. Okay, yes, hello. Hello, please, hello.
Good afternoon, sir.
Good afternoon, yes.
Motion of a rocket, can I apply in jets?
Yes, you can very much apply in jet. Yes, the same thing you can apply, but the analysis will be different. The same analysis you cannot apply. You have to apply the Reynolds transport theorem for jet engine. You can see examples in my book, fluid mechanics book. You can see very well an example of jet engine also, which no, you can very well apply to a jet engine. Again I tell, just now I have explained this, that in a jet engine what happens if you take a control volume of the jet engine. In a jet engine, air is coming in to the control volume, because a jet engine takes air in from the ambient and the products of gases, that means the jet goes out. So you have to consider both inflow momentum, the outflow momentum. Okay. In case of mass, you have to consider the inflow mass and the outflow mass. If this is at steady state, the inflow mass and the outflow mass will be same. Okay. It is exactly not same, because in outflow along with air there will be fuel. Sometimes what in our analysis, usual analysis, we neglect it, because in a gas turbine engine or an aircraft engine, the mass flow rate of fuel is very less as compared to the air. The ratio of air to fuel mass is almost in the range of 60, 70, 60 to 100. So therefore, I am sorry. So therefore, what we do, so therefore the mass flow rate of fuel is neglected, and sometimes we can, in most of the cases we can consider it is a steady flow, the amount of air which is coming in through the intake nozzles is going out through the propelling nozzles. So therefore you have to take care of inflow and outflow momentum, and accordingly you have to analyze through Reynolds transport theorem. So similar to nozzle, similar to rocket you can do, but not exactly in the same way. ঠিক আছে তো? One three 18. 1318. Yes, good afternoon. Yes, please.
Sir, first of all, I would like to thank you for clearing our concepts on Reynolds transport theorem.
Okay,
I
thank
have
you.
just one small doubt.
Yes.
That we take dn by dt, where n is any property. I just wanted to know that whether there is any constraint to the choice of property.
No.
For example, can we apply this theorem on the pressure change through a flow?
No, the property has to be an extensive property. This can be applied to an extensive property, okay, which are conserved. Conserved extensive property. Reynolds transport theorem you have to apply for conserved extensive property, okay, like mass, energy, momentum, linear angular momentum, like that. You have to apply the entropy, the conserved extensive property. Though entropy is not conserved the way energy is conserved, because there is a destruction of entropy, but any extensive property conservation can be dealt by Reynolds transport theorem. Pressure is not an extensive property. Okay?
Okay, thank you, sir. We have one more question.
Okay, please.
Hello?
Hello, please.
Is this valid for two-phase flows also?
Yes.
What you have taught?
Yes, yes. Reynolds transport theorem is a general transport theorem. In two-phase flow, you have to define the property accordingly. In a two-phase flow, things are not homogeneous, so velocity has to be defined properly, the mass has to be defined properly. But as far as the theorem is concerned, with its nomenclature, it holds good for two-phase flow definitely.
How do you take care of, when the phase changes, say,
That is a different, that is a different, that is a, look, that is a different physics, that one has to know how you will define the momentum changes, all these things. This will be definitely much more complicated. Okay, but the Reynolds transport theorem is a classical theorem. Okay, there is no restriction over it. That depends upon how do you define a system. If you can define properly a system and you can specify the system property, you can define a control volume and you can specify the control volume property or its variation in consideration of the physics of the system and the control volume, you can invoke Reynolds transport theorem. There is no restriction to this classical theorem. Okay.
Okay, thank you very much, sir.
Okay.
Thank you.
Okay. One 1184. Audible, no? You are not audible. Oh, you are not audible. You are not audible. Please, you are not audible. Next. Next, okay. Hello. One 1303. Yes. 1303.
Sir. Sir, good evening.
Good evening, yes.
Sir, I have a doubt on the problem you have done
Yes.
on the conservation of angular momentum.
Yes, please tell.
Conservation of example you have done in the conservation of angular momentum.
Yes.
In the term 2, the product of the relative velocity and dA and area
Yes.
is taken as Q. Is taken as Q.
Yes.
But you have mentioned in the beginning that Q is taken as divided to one nozzle.
What we have?
Sir, why you have taken Q instead of Q by 2?
Instead of Q by 2 we have taken. No, I do not understand your question. Again, can you explain? Hello?
So in the water sprinkler problem,
Yes.
Second part,
Yes.
the product of ERA is taken as Q instead of Q by 2 you have mentioned in the beginning of the problem.
If I have written, there may be an inadvertent mistake. In one limb it will be Q by 2. In one limb, yes. When I have used, please listen to me. In the second term, first of all, in the lawn sprinkler problem, please, in the lawn sprinkler problem, the second term is, in that case, VR dot NDA. Please listen to me, that in the second term, R cross V into VR dot NDA, in that case, VR dot NDA will be Q by 2. Okay. This VR dot NDA in the second term will be Q by 2. That is the flow rate, volume flow rate coming through that limb. Definitely it will be Q by 2. You just correct it. So I cannot just tell you what I have written. That will be Q by 2. Total flow rate, if total flow rate is specified as Q, then the flow rate through any limb will be Q by 2, which will be VR dot NDA over the control surface, where the control surface is the area of that, of the nozzle or of that limb, of the nozzle of that limb. Okay, that will be Q by 2. Okay.
Sir, one more question is there, sir.
Please, please.
Hello, one more question, sir.
Yes, yes.
Sir, we have derived the basic laws considering a small rectangular small part of the fluid. Now again, using Reynolds transport theorem also we have derived, for example, the continuity equation. So which one is the Eulerian and which one is the Lagrangian, this thing, sir? And one more thing is that how much credible it is, which equation will be more credible? What is the difference between those two?
Which two? One is the Reynolds transport theorem, another one is what?
Considering small element, derivation of continuity equation and
See, just a minute. The continuity equation, okay, please listen to me. What is going on there? You see, the continuity equation is derived with respect to a control volume. Okay? Because there is a mass flux coming in, going out. This is not a system approach. So whenever we consider an element of fluid, that is nothing but the elemental control volume. That is the differential approach. And when we derive it, we make this limit delta x, delta y, delta z. If these be the dimensions of the element or elemental control volume, then they tend to 0. This is a differential approach. Whereas when we do with integral approach, that means we take over an area, again I am telling over a domain, and Reynolds transport theorem deals with the integral approach. If we apply Reynolds transport theorem to conservation of mass, then the mass conservation of mass equation which we get for the control volume, that 0 is equal to net rate of increase of mass in the control volume plus net rate of mass efflux from the control volume. The statement remains same, but the mathematical expression is for is in integral form, whereas in differential form the continuity equation applied to an elemental volume is in differential form, where we arrive at del rho del t plus divergence of rho v equals to 0. Okay, এবারে শেষ করে দাও, আর আমার চেঁচাবার ক্ষমতা নেই, 1 ঘন্টা হতেছে, আর এই কোশ্চেন করলে চেঁচাতে হচ্ছে।
Good evening, sir.
Yes, good evening.
Hello. Good evening, sir. Sir, my question is little bit long. You see, when we are defining Lagrangian approach, then we are telling S equals to S naught and T, that is the S is the function of initial position vector and the time. Then we can put this particular equation in terms of word, and we are telling if somebody is standing, or let's say a policeman is standing on a square and somebody put traffic rule, then if the policeman chase that person and then cut his challan, then that is what the Lagrangian approach.
Yes.
Similarly, if you consider a case of Eulerian approach, then we are telling in a class that okay, if somebody is designing infrastructure for a square and he would like to analyze how many vehicles are coming at that square, how many four-wheelers are there, how many trucks are there, how many two-wheelers are there, then that is a Eulerian approach. So what I am trying to emphasize, by this way we are trying to put these two approach in terms of a very common live example problem, or rather live example this thing. So we are correlating. So since this theorem seems to be little bit difficult, or you can say in mathematical form we are writing del by del t of change in control volume plus control surface, means influx and outflux. So if we consider India as a country and their boundary as a control surface, so can we put this particular Reynolds transport theorem in that perspective in terms of, let's say, population or something else, some goods which we are creating or we are exporting or something like that, then it may be more connecting to the student. Can you emphasize on this, please, sir?
No, you see, you are very good. I appreciate the way you think all these things. Now, first of all, I tell you, it is very nice that the way you have explained this Eulerian and Lagrangian approach. In Lagrangian approach, we follow a particle, and this way we follow all the particles. In Eulerian approach, we stand fixed at a point and study the particles passing through the points, and that way we tell many people to stand at a fixed point, don't move, and just go on tracking the particles which passes through you, and this way all the people can track all the particles. This is the Eulerian approach. Very well understood and very well explanation that you give to the students. Now regarding this Reynolds transport theorem, as you tell, okay, if you consider India as a system, not system, as a control volume, because the population is going out, population is coming in, you consider the population as a flux, that is true. But try to understand, when you apply Reynolds transport theorem, first of all you have to find out the property. First of all you have to find out the property whose conservation principle you have to find out, whose conservation principle is to be explored. Okay, first of all you have to fix the property which is conserved and whose statement with respect to a system where there is no flux, mass flux across it, is well defined. Then you relate that with the control volume, because Reynolds transport theorem, try to understand, does not tell or evolve any physical law. Physical law is known. For example, mass is conserved in a system. The net rate of change of momentum or the rate of change of linear momentum, for example, of a system equals to the force impressed on the system. The rate of change of angular momentum, these are all conserved property, equals to the net moment acting on the system. The rate of change of energy within the system, that is the internal energy of the system, equals to the energy interactions by the system with the surrounding by thermodynamics first law, del Q minus del W. All these informations regarding the conservation of energy within the system, conservation of momentum of the system, conservation of mass of the system are known, and then we apply it to a control volume where the mass fluxes are there across the boundary, and due to this mass flux all these properties are taken away coming in. That means property fluxes are there because of the mass flux. Energy is coming in, energy is going out, momentum is coming in, momentum is going out. Then we relate these two things. So therefore, if we have to apply to any such situation, so first of all you have to identify the property, that extensive property, and its conservation laws has to be known a priori with respect to a system. Okay, then you can apply the Reynolds transport theorem. Reynolds transport theorem does not evolve any physical law. First of all, you have to know the physical law, you have to formulate the physical law applied to a system. For example, the population is changing in a country, and if we make the barrier of the country such that nobody can go out, nobody can come in, so population will change in the country. Definitely population will change because of other things, as you know. Then we have to make a physics how this population change is related to other parameters. Then we will translate this to control volume. Okay. 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 No, this is the last question. Another one, because 1250 না আর বকা যাচ্ছে না প্লিজ
Hello sir, am I audible?
Yes, audible.
Sir, is there any difference between static pressure, thermodynamic pressure and mechanical pressure?
That I will not answer, that has been already explained by Professor Shumon Chakraborty. So please ask Professor Shumon Chakraborty. There is a difference between thermodynamic pressure and the mechanical pressure. Okay, there is a difference between the static pressure and the mechanical pressure. All these things will be told by Shumon Chakraborty. Please don't ask me question, I am not going to answer it. Please never mind, Shumon Chakraborty will do it, Professor Shumon Chakraborty. Okay, I think today he has taught mechanical pressure and he has emphasized what is the difference. What is the difference between the, because the mechanical pressure takes care of thermodynamic pressure plus the deviatoric pressures due to the fluid viscosity. It is the stress, normal stress. Okay, this will be explained by Professor Shumon Chakraborty. Okay. One more question. No, this way. 1064, 1064, yes.
Hello. Good evening, sir.
Good evening.
Good evening, sir. Hello.
Good evening.
Sir, my question is,
Good evening.
what is the need of Reynolds transport theorem? Sir, what is the need of Reynolds transport theorem?
So I have told this thing again and again. I am
Sir,
telling.
what is the need of Reynolds transport theorem?
What is the need? What is the need of Reynolds transport theorem?
Yes, sir, need.
So this is telling from the beginning, you are asking this question at the end. How do you analyze the conservation of momentum for a control volume? How do you analyze the conservation of energy for a control volume? If you do not know that rule, if you do not know the principle, I told at the beginning of the class and many a times I am telling, how do you analyze the conservation of momentum for a control volume? You have to analyze for a control volume. For example, there is a compressor, fluid is coming in, angular momentum is coming in, fluid is going out, the angular momentum is going out. How do you find out the force exerted on the shaft of the control volume approach? So you cannot tell that rate of change of angular momentum is equal to the moment. That is for a system where there is no mass flux. So then you have to know the corresponding statement for the control volume. Okay, thank you. No, 1047.
Hello, sir.
Yes, please.
This is Professor Marikatti, workshop coordinator, sir. Good evening, sir.
Okay, thank you.
Am I audible?
Audible,
sir?
audible, audible, audible.
Yeah, our one of participant has one question, sir.
Please,
Question 8, sir.
please, please.
Good evening, sir.
Good evening.
Am I audible? Sir, my question question is from Reynolds transport theorem.
Yes.
So, the government know the was it different between the system based approach and the control volume approach?
This has been told. System approach means you have to take a system and you have to analyze based on the laws applied to a system, that is system approach. And control volume approach is that you have to take a control volume and analyze the system by application of the physical principles applied to control volume. Many a times we know the physical principles for system, but we do not know the physical principles for control volume. Control volume approach means we have to take a control volume and analyze the situation, analyze the physical processes. So when you take a control volume, then you have to know the principles applied to control volume. When you take a system, you have to know the principles applied to a system. So that is the difference. System approach means take a system and analyze the process with respect to the system, where you have to know the principles applied to system. Similarly, for control volume, you have to take control volume and analyze the process with respect to the, by knowing the principles applied to control volume. And Reynolds transport theorem is invoked to relate, if you do not know the statement or the principle with respect to a control volume, whereas you know that with respect to a system, in particular to the conservation of an extensive property, then we invoke Reynolds transport theorem, which relates these two. That is simply as simple as that. I told you. Okay. If you have any questions, please upload in the Moodle forum. Okay. Oh.
Hello, sir. Excuse me.
Okay, thank you. Today up to this.
One more question.
Hello. No, this is the last question.
One more question, sir.
Okay. Okay, please.
Okay.
Please.
Hello.
Yes.
Thermal stratification occurs in different layers of atmosphere.
Yes, but this is beyond the Reynolds transport theorem. You ask question on Reynolds transport theorem. Okay, if you have any questions, please upload in the Moodle forum and we will answer it. Thank you. Thank you.